Okay, welcome to the last lecture of the module. I left you last time with looking at this redshift slice. So recall we're at the center here and looking out through a plane in the sky. Each dot is the redshift of a galaxy. And I asked you to look at these strange fingers of God type phenomena here, which are associated with the peculiar motions of galaxies within clusters of galaxies, where the local gravitational influence is stretching their velocities out along a radial spoke pointing outwards. So you can see several of them on here. And asked you to have a look at this one and sort of estimate by eye, really, what kind of uncertainty on the distances of the galaxies within that cluster you might get if you just naively interpret the redshift with Hubble's law like we normally do. So again, just by sticking a sort of ruler on here, recall the scale goes out to 12,000 kilometers per second, starting at 0 in the center. So you need to measure the, what I did was measure the full extent of this line, scale it to this one, and then divide it by 2. Okay, so you've got a plus or minus delta V on the velocity of the average velocity here. Okay. So I estimated that the delta V here was about 2,500 kilometers per second. Again, just roughly estimating. The mean velocity of this sort of particular spoke here is about 6,700. Okay. So we know that V equals h naught d, so this is Hubble's law. So if we just look at sort of fractional errors in this is just a linear formula. So the fractional error on the distance would be the same as the fractional error on the velocity. And so you can just take delta V over V to be this, which is about 0.4. Or another way of looking at it is that you could get a 40% error on the distance in some of these galaxies here if you just naively interpreted the velocity as purely being due to Hubble's law instead of being affected by the gravitational attraction pulling the galaxies around and giving them these high peculiar motions within the cluster. And of course then giving rise to this finger of God phenomena here. Okay, and we'll come back to use this velocity a bit later on in the first example in this lecture. So we'll come back to this later. Yeah. So in this final lecture, we've come to the intriguing topic of dark matter. So those of you who did attend workshop 5 have already looked at some of this. So I'm going to quickly go over rotation curves of galaxies because we've already covered that in workshop 5 where you were putting it into action already. So I'll just recap the main points. I'll then look at 2 other ways of we can measure or get the measure of dark matter. So these will be using whole clusters of galaxies. So actually pretty much the example I just gave. And then we'll finish up touching on gravitational lensing is another sort of interesting idea where we can probe this dark matter phenomena. Okay, so let's quickly run through this same idea of galactic rotation curves that we looked at in workshop 5. So the general idea here is that when we look at a galaxy in starlight, then obviously there's a distribution of matter in the stars, but as we get out towards the sort of more outer parts of the galaxy, we can see that most of the visible matter, if you like, is concentrated in the central region of the galaxy. That's where most of the starlight comes from. And so, therefore, we'd expect most of the mass of a galaxy, if it was just purely dominated by the stars that make it up, to be reasonably in towards the center. Now, if that is the case, and we'll sort of rehearse the mathematics in a moment, then we would expect the rotation speeds of the galaxies should start to fall off with increasing radius in the outer parts of the galaxy, because most of the mass that's constraining the galaxy and causing the stars to orbit around in circular orbits should be inside of those radii in the outer parts, and therefore there shouldn't be any, if there's no more increasing mass, then all of the mass of the galaxy would be in effect acting through a center of mass at the center of the galaxy, and therefore it should start to fall off. So just a reminder, I showed this in workshop 5 as to how to actually, one way of measuring the rotation of a galaxy. So these are spiral galaxies, so the only ones that really have this ordered rotation are the only ones that we can sort of do this simple kind of exercise on. So here's our galaxy. You can see spiral arms here. This is another one of the local group galaxies, M33. So as you can see, it looks like it's rotating around sort of this way. Okay. And in the blue patchy light here are the clouds of atomic hydrogen gas, H1, measured by the 21 centimeter line, so therefore we can get Doppler shifts from that as well. And on the right, we see the color-coded velocity information from that 21 centimeter line. Indeed, it's showing that this side is going away from us. Is that right? I've got the galaxy going around the wrong way. Okay, I couldn't see the spiral arms there, so it's going around that way. It's a strange galaxy, this one. It hasn't got a proper spiral arm. So this side's coming towards us, this side's going away from us. But you can see this, the nice rotational velocity pattern in the galaxy. So from that, we can measure the rotation of the galaxy. But so, as we've seen for the Sun in the Milky Way, we believe that we're going around in a circular orbit, and we can prove that that most stars in spiral galaxies are going around in circular orbits. So just going back to basics, if we look at circular motion, you've got a centripetal force and a gravitational force that's delivering that centripetal force to keep everything moving around in a circle with a radius r and circular speed v. So here v is the orbital speed, the speed at which stars are orbiting around the galaxy. Big M is basically the mass inside this radius, as we talked about in workshop 5, and little m, you can think of it as the mass of a star or a gas cloud. It's the test particle that's going around in a circle. But you can see it cancels out, so it doesn't matter what it is. So if you just make v the subject of this formula, so in this case, if most of the mass is inside your radius r, then your velocity should start to fall as 1 over the square root of r. Okay? And this is referred to as Keplerian rotation. So this kind of velocity law is Keplerian rotation. And it's exactly how the planets in our solar system orbit. Okay? If you go back and look at Kepler's laws for planets in our solar system, kind of for binary stars in general, then this is what you get, okay, if the mass is dominated by some central source. Okay. So that's what we'd expect when you get to the outer parts of the galaxy. All the mass would be inside the radius. But that is not what is observed. Okay. So again, I'll remind you in a moment with some pictures, but basically the rotation curves that we see, the rotation velocity is constant out to basically as far as has ever been observed in any spiral galaxy, including our own. Okay. Recall that in the Milky Way, we had this rotation speed of just over 200 kilometers per second, and basically that was constant throughout the galaxy. And as I just showed you, H1 rotation curves can go way beyond where the stars are. Okay. So that you're just looking at the sort of cool, cold atomic hydrogen gas that sits outside of the, further out than where the stars are, and that's still flat as well. Okay. So at that point, there's clearly no stars there, and the amount of mass in the hydrogen gas you can measure, and that's pretty small. The mass of the sort of interstellar gas in a galaxy like our own is only about 10% of the mass of the whole stars, so that's not really contributing significantly to the gravity. So there's something else going on here. And whatever it is, okay, you prove this to yourself in workshop 5. We can't explain it with the stars, you can't explain it with the gas. So basically, it's something we can't see, and that is where the term dark matter comes from. So it's dark because we don't know what it is, we can't see it. It's matter because it's got mass, so it's got a lot of mass, right? There's more mass in this stuff than there is in all the stars. Okay? And it's also much more extended in its sort of distribution, spatial distribution, than the bits of the galaxy we can see, the stars and the gas. It's got to be much more extended than that. So, for instance, for our own Milky Way, it must be extend, on scales much, much bigger than 100 kiloparsecs, which is out to which we'd see the sort of globular clusters, etc. And recall that the next galaxy along, M31, the Andromeda Galaxy, is only it's less than a megaparsec away. So the dark matter is sort of filling in quite a lot of this space, but it's still concentrated. Basically, the whole reason that there is a galaxy like our own here is because there is a concentration of dark matter that is pulling in the sort of normal, what we would call baryonic matter, the stuff, atoms, protons, electrons, that stuff we know about. It's the dark matter that's pulling it all in there and giving rise to the galaxy. So just coming full circle, pardon the pun, then here is our rotation curve for the Milky Way again. So I showed you this before. Okay, so you can see here it's flat at around about just over a couple of 100 kilometers per second. If anything, it's going up. And yet, once we get out here, way past the sun, most of the visible matter in our galaxy is in here. So we would expect the rotational speed, v, to start to go down as 1 over the square root of r. So a curve looking like this. But you can see that the rotation curve does no such thing. Okay. And the same is true for every other galaxy we've ever looked at. Okay, so here's, again, from workshop 5, some examples of these other rotation curves. And you can see that they're all pretty much flat. Okay. There's no sign of a 1 over the square root of r fall off, telling us that there's no more mass outside of this radius to measure, to keep things moving around. Another way of looking at this kind of evidence is to say that if we only had the visible mass in one of these spiral galaxies, there's no way that the stars out here could be rotating this fast and still be bound to the galaxy. They'd have flown off into galactic space a long time ago. So something else must be holding them there. And it's something that's extended on much larger scales than these, tens of kiloparsecs. It must be on scales of hundreds of kiloparsecs. And in workshop 5, then we worked out that there was basically 5 times more dark matter in a sort of typical spiral galaxy, individual galaxy, than there is visible matter, i.e. the stars. Okay, so that was dark matter in individual galaxies, like spiral galaxies, as probed by the rotation of those galaxies, but effectively you can do the same thing with elliptical galaxies. There you don't have the organized rotation, so you'd have to measure the speed of sort of individual stars and work out how they're orbiting around, or you could do it with looking at how globular clusters orbit around a galaxy. Ellipticals have those just the same way that spiral galaxies do. So again, you'd be measuring the speed of individual objects that are probing, being controlled by the gravitational potential well, and you can still measure the amount of dark matter in there. And so the same issue for elliptical galaxies or regular galaxies. They're all dominated by dark matter. So now we want to go up in scale again to clusters of galaxies. Okay. And we get the same problem, in fact, even worse, here. Okay. So same idea. Okay, you've got a cluster of galaxies like the one in the background picture here. There's a center of mass, effectively, in a cluster of galaxies, and all the individual galaxies are moving around under the gravitational influence of all the mass that's within that cluster. So therefore, again, we can use the galaxies now a bit like test particles to try and measure the mass of the whole cluster of galaxies by measuring the speed at which they're moving around within that gravitational potential. So here I'm going to do a very hand-wavy dimensional derivation. So this is very approximate. Okay, a proper treatment gives you a similar answer, but the answer varies by a factor of 2 or 3. But you get the idea. Okay, so let's just equate the kinetic energy of a galaxy with its gravitational potential energy of the cluster. Okay, so the kinetic energy of an individual galaxy that is moving around within the gravitational potential well of the cluster as a whole. So as I said, if you look in textbooks, you'll see a slightly different numerical factor, but it's dimensionally the same. So here we go. Let's equate kinetic energy with potential energy, because we can do that with the physics you know at the moment. So kinetic energy of a galaxy moving around. So the galaxy has got a mass little m now, and is moving around with a speed v. And big M here now is the mass of the entire cluster of galaxies. Okay, and R is some measure of the size of the cluster. So really, like, sort of, again, if we consider a galaxy that's sort of on the outer edge of one of these clusters, then R is like the size of the cluster, size of the orbit, whichever way you want to look at it. Really. You can see it's actually very similar to the Keplerian argument. It just differs by a factor of 2 here. Okay. Okay. So you can use this formula. In fact, you can turn it around. This is telling you what speeds individual galaxies should move around if you've got a cluster of mass m, size r. But in a moment, I'll ask you to measure the mass of a cluster using this by looking at the typical speeds of galaxies that we saw at the beginning of the lecture and adopting a size. And we can measure the mass. So here we find the same problem again. The observed speeds of the galaxies, so that's what we just talked about in the last lecture. Basically, this is the idea of peculiar motions. How fast are your galaxies moving around within a cluster due to the gravity within that cluster? And those speeds are much larger than the visible mass in the galaxies can explain. So we'll just go back to the formula here. If you just added up all the mass of all the stars in all the galaxies and put that in here, you would come out with a much lower speed than what you actually observe. Okay. And same, turn that argument around. If the mass of the cluster was just the visible mass, all of these galaxies would have flown apart a long time ago, because there's clearly not enough gravity to hold them together. They're not gravitationally bound by the visible mass. So again, we must require some extra mass, and it's this time, and this is kind of common with dark matter, the bigger the scale you look at it on. So here we've gone up from the scale of an individual galaxy, a few tens of kiloparsecs across, to the scale of a cluster. So we're now up to a megaparsec across. The amount of dark matter required is even more again. At least 10, maybe 20 times more than the visible mass is required to hold these clusters of galaxies together. Okay. So it's mysterious stuff. Okay. So, and it only really comes in, so that sort of the opposite of that argument. We only see its effect on cosmological scales, really, on large scales. I mean, you can see it in individual galaxies, but when we're talking about the solar system, or how stars are held together, we don't need to worry about dark matter there. It doesn't matter on very, very small scales. I mean, presumably it's everywhere, but it's the scale that it's distributed on is so large that in a local environment on those sort of small scales, you can just ignore it, and Newtonian mechanics works perfectly well. Everything to do with the motion of the planets around the sun is perfectly well explained by just looking at obviously the visible mass of the sun, and we can send probes accurate to a few meters all the way to Jupiter without worrying about dark matter. So chance for you to put that formula in action, the one I was just talking about here. So make M the subject of this one, and put in the delta V, if you like, that we had at the beginning of the lecture. Okay, and here just assume that the R, the size of your cluster, just assume it's got a radius of 1 megaparsec, just for sake of argument. Okay, and see if you can get an estimate of the mass of this particular cluster here, the one that had the very large distribution of velocities here, so that to give you an idea of how that works. Okay, and if you work it out in solar masses again, that would be useful. You can give you something to compare to. Okay, have a go at that, and then come back after the break.